sense the evolution of relationships between things which are evolving rather than the evolution of the system as a whole unit. And I'm coming to the conclusion that there's a simple self-organizing principle going on which is helping adaptation occur that's not natural selection. So I wanted to see if I can produce a model which separates the natural selection out of it altogether so that we can see what's left. I'm aiming for a model that's as simple as possible but not more so. Tell me if I've gone too far. So my goal is to demonstrate adaptation in a trivial physical system where there's no natural selection involved. So I need a definition of adaptation. Now, I don't want this to be to exclude other definitions of adaptation. I want to say that it's just a sufficient one. So I'm going to say something like an ability to find a system configuration that minimizes conflicting constraints or inefficiencies within the system and between the system and the environment. A sufficient condition, a sufficient demonstration would be a capability to solve a non-trivial constraint optimization problem. Now, I know that a lot of you will be unhappy with the idea that, say, evolution by natural selection, which is an adaptive process, necessarily solves constraint optimization problems, but I'm not saying it's a necessary condition, I'm saying it's a sufficient one. If you have a process which could do that, we would be happy to call it adaptive. Well, actually, that's still a little bit weak because, like a ball rolling down a hill is a physical dynamical system which you can interpret, depending on the crinkliness of the hill, as a physical system which is solving a constraint optimization problem. So I'm going to modify it slightly to say the capability to solve a non-trivial constraint optimization problem better than a hill climber is a demonstration of adaptation. So my question then is, can physical systems perform adaptation by that definition? So we know that physical systems can perform adaptation by that definition because evolution by natural selection can do that, brains can do that, but I want to know whether any non-designed, any non-designed, non-evolved systems are capable of doing that sort of adaptation. Right? So of course I claim that they can. A dynamical system with plastic interactions between components, and I'll define that in a very simple way, will exhibit adaptation spontaneously if it's conditioned appropriately, and the conditioning is fairly straightforward as well. It basically means perturbing it at an appropriate time scale. So I'm going to present an example of a system which finds configurations that minimize conflicting constraints or inefficiencies within the system better than a hill climber can. It performs effective optimization in the sense that it does better than local optimization. And that occurs in this system without any natural selection, because there's no reproduction of the system. The system isn't being replicated at all. It's selective in that sense. Now, the way that it works exploits a mechanism which is equivalent to Hebbian learning in a neural network, but it's without assuming that there's Hebbian learning there. It doesn't require natural selection to design the system or to design the mechanism of Hebbian learning or to operate its mechanics. Right? So what sort of dynamical system can I talk about? Let's talk about a dynamical system, let's call it A, that has a network of variables which are, where each variable's state, binary state, is non-linearly dependent on the sum of forces from other variables and the environment. So think of it as a system of particles connected with levers and springs or something like that. So here's an example. We've got particles moving up and down on the rod, so they have binary state here, and they're being pushed around by a system of springs, so the springs are represented by the lines connecting the particles. And the spring's natural length is when it's brown, not red. Can you see the difference in the colours? Yes, you can see the difference in the colours. And the idea is that if the two particles that are connected by a spring are in opposite states, then the spring is relaxed. Whereas if two particles that are connected by a spring are in the same state, then the spring is bent or in tension. So the springs which are in tension are shown in red. So if I was to ask the particle which has the arrow on it, would you like to move, i.e. are the sum of forces acting on you causing you to change your state, then this particle might change state, which would release the tension in the spring that was to the left of it, but it would create a tension in the spring that was to the right of it. Now, I'm not actually going to do it in a one-dimensional array like this. I'm going to do it in a random network of springs, where the number of connections that each particle has might not be the same. So the sum of tensions are unlikely to be exactly symmetric as they were in the one-dimensional case. So release of energy from tension from one of the springs may create tension in another spring, but actually it's always less in total if it's a natural physical system that has detailed balance. So that was just the other particle moving to another configuration. So some configurations of the system have lower total tension or just lower energy than other configurations of the system. And if we were to set the system to a random initial configuration and just let it relax, it would find some locally minimal configuration in that space of possible configurations. So here's some runs of what that does in its natural sort of state. There's no adaptation here, I would say, because this is exactly like a hill climber, and I needed to do better than a hill climber. So is this the point? Yes. So the system configuration started a random initial configuration. This is just 10 example runs of the system, how the energy decreases over time. Because it's a system which has symmetric connections, which is natural in a system of particles connected by springs, you know that it's going to have only fixed point attractors ultimately. But there are many different locally optimal configurations where in any one of these configurations none of the particles have sufficient forces on them to make them change state, and yet some of the springs are still in tension, and different local optima then correspond to a different number of springs remaining in tension, and hence being higher energy. So the behavior of this system is exactly equivalent to a stochastic hill climber searching by doing bit flips to see if I change the position of one of these states, would it decrease the energy of the system. So local hill climbing minimization, hill descent, in the space of configurations on the energy function would produce exactly the same behavior. Okay, so now I'm going to add to this system something very simple. Suppose that the mechanisms that enact forces between the components, i.e. the springs, wear out over time, and they wear out in proportion to the resistance they're put under, or the tension that they're put under. So the relationships between components are imperfectly elastic. These are not perfect springs. They're slightly plastic, and they deform over time, and they deform in a way that's proportional to how often you bend them. Yeah? So for any spring, at any time, if it's in tension, reduce the strength of the string a little bit. Yeah, so the more often I bend it, the less springy the spring is, and the more plastic it becomes. So that's the only change that I'm making to the system. So now my claim is that if a system of that type is appropriately conditioned, which I'm going to define in a minute, then the system will exhibit adaptation in the sense that I defined before. I.e. the modified system B, it's called the original one A, and the modified one B, right, that's just the same system but with the springs bent a bit. We'll find configurations that solve the original constraints between the system better than A did. Okay. So let's quantify that just a little bit to be clear about how we know when it's worked. So different configurations of the original system A are more successful than others at minimizing the tensions between the variables. They're just more successful than others at minimizing energy. There are different local minima in the energy function. So let's record the value of all of those configurations, just so that we've got that clear, right? So for all possible configurations of the system, what energy do they have? So some of those configurations will be locally optimal in system A, and some won't, but that's fine. We'll just record them all. So in system A, let's set it to a random configuration, and let's let it equilibrate. I've already shown you what those dynamics look like. And from different initial conditions, it will reach different local optima. So there's a distribution of local optima that system A finds in that energy function. So let's call that distribution of system A star. Okay, so now let's allow the system to be conditioned according to the self-structuring protocol which comes on the next slide. And now that because the springs have been changed by that conditioning, let's call the system B. Now that system, if I set it to a random initial condition and let it relax, it finds a locally minimal configuration. It turns out it's easy to show that this type of conditioning on the springs will still produce a system that has only fixed point attractors. And let's call that distribution of attractors B star, and then we'll just say, well, if the average value of the configurations in B star is less than the average value of configurations in A star, we're minimizing because we're trying to find low energy configurations here, then the system has improved its ability to find configurations that satisfy the constraints between its variables.